Hello and welcome to video 8 of Module 5. In this video, we'll be discussing events that are mutually exclusive. So let's start with a definition so we know what that means. Two events are mutually exclusive if they cannot happen at the same time. So, for example, suppose I want to draw a card from a deck of cards. Is it possible for me to draw a card that is both hearts and a black card? No, because all cards that have hearts on them are red cards. So drawing a card that has hearts on it and drawing a card that is black are mutually exclusive events. They can't happen at the same time. However, suppose I was looking at drawing a card that has hearts on it and drawing a queen. In that case, both of those events could happen at the same time. You can have a queen of hearts. So drawing a hearts card and drawing a queen are not mutually exclusive because they could happen at the same time. Now, when we have mutually exclusive events, we can adjust our formulas a little bit. So, in particular, events that are mutually exclusive cannot happen at the same time. So the probability of them happening at the same time is 0. That's where that first equation comes from. The probability of x and y is always 0 for mutually exclusive events. In our formula for the probability of x or y, we originally had the probability of x plus the probability of y minus the probability of x and y. But if the events are mutually exclusive, the probability of x and y is 0, so we don't have to write it in the formula. In other words, for mutually exclusive events, you can just add up the probabilities in order to determine the OR. Again, you want to make sure that you know the events are mutually exclusive before you use these formulas. If you don't know whether two events are mutually exclusive or not, you cannot use these formulas. You have to use the bigger ones that we spoke about earlier. Let's do a couple examples. Let's let X represent the race of a person who's incarcerated at a federal prison. The probability distribution to the right is based on values found on the Federal Bureau of Prisons website in September of 2016. Let's think for a moment whether these events are mutually exclusive or not. In other words, just generally speaking, could somebody be more than one race at a time? Yeah, you can have people that are more than one race. So because in reality races overlap, these events are not mutually exclusive. However, let's examine our frequency distribution here. In this case, remember that your frequency distribution lists all the possible things that can happen. So in this frequency distribution, none of the options involve more than one race at a time. What that means is that these events are being treated as though they can't overlap. And you see this a lot of times in surveys. They'll say pick one of the following. So unfortunately, things that in real life are not mutually exclusive are often treated as mutually exclusive. So for purposes of this example, we're going to treat race as if you're only allowed to be one for this particular study. With that in mind, let's determine some probabilities. Let's determine the probability that somebody in this study was able to list both Asian and white. Well, since these events are being treated as if they're mutually exclusive, that would mean you can't have two things happening at once. In other words, you can't have somebody list both Asian and white. So this probability will be 0. Let's do another one. Let's determine the probability that somebody was not white. Now there are a couple of different ways that you can approach this probability. You could say, well, based on the information that was collected, the races that are not white were Asian, Black, and Native American. So the probability of not white could be thought of as the probability of Asian, or the probability of Black, or the probability of Native American. For mutually exclusive events, when you have an OR, all you have to do is just add up those probabilities. So we can add up the 0.015, the 0.378, and the 0.021, and that will tell us 0.414. An alternate way to determine this probability is to use complements. Remember that the probability of not white is the same as the probability of the complement of white. And the formula for complement says just subtract it from 1. So to find the probability that somebody is not white, I could just take 1 and subtract 0.587. Take 1 minus the probability of white, and I end up with a 0.413. Now, if both methods are correct, we should end up with the same answer either way. And we got really similar answers here, but why are they different? Well, the answers are going to be a little bit different here because in this probability distribution, these decimals were rounded values. So the reason we're getting slightly different answers is because of just rounding error. So either of these two answers would be a correct solution because both of the methods used to find them were correct methods. Let's do one more example. So let's determine the probability that somebody from this group is Black or Native American. Since the events are being treated mutually exclusively, we can just add the probability that somebody is Black to the probability that somebody is Native American. In other words, we can just do 0.378 plus 0.021, and when we add those up, we end up with 0.399. And that's it. That's all we have to do. I hope you enjoyed this video about mutually exclusive events. This video actually concludes Module 5 for discrete probability. The next module is going to be about continuous probabilities, so we'll be using some different techniques there. Thanks for watching, and have a fabulous day.